Hello, Mr. Simpson back here with our third video for Chapter 13. In this video, we're going to take a look at shifting equilibria, particularly Le Chatelier's principle. Please pause the video to copy your learning objectives in your notes. Okay, you can see here the definition of Le Chatelier's principle. When a system has established equilibrium, that equilibrium can be disturbed, which means then the system will begin running, again, the reaction in the reverse or in the forward direction to return to equilibrium, all right, counteracting the disturbance that happened. Okay, so basically at equilibrium, your Q equals your K. Disturbance causes a change in Q. The K doesn't change, right? That's the equilibrium constant. That does not change. So the system will shift right or left, forward or reverse to get back to the point where K equals Q. Okay, so I'm going to talk for a second about ways in which you can disturb a system in equilibrium. But before we do that, I want to just emphasize again this point about the shifting that occurs. So at this point, we have established this idea that the yields arrow is actually a reversible reaction arrow. So the reaction can go either direction. So what happens here is when I have a system in equilibrium, it will, and it is disturbed, it'll shift on its own either in the forward direction or the reverse direction to get back to equilibrium. Okay, so really our task here is to understand the disturbances, when a disturbance happens, which way it'll shift, right or left, and what that means for our reaction. With regards to what does that mean, remember, let's just say I have a reaction going in this direction. Anything in the front of the reaction are products. Okay, and those products are being produced, so there's making more of them. So concentration of the products, of anything on the product side, would be increasing. On the back side of the arrow, those are our reactants. Reactants are being consumed or used, so the concentration of the reactants are decreasing. Okay, so that leads us to our first way to disturb a system at equilibrium. So the first way we can disturb our equilibrium is by adding or removing a reactant or a product. Adding or removing a reactant or a product. So if we think about what's happened here, so let's just say, looking at our reaction here, let's just say I had a situation where I added A. Okay, so now if you think about what happens is, now you have too much A. You have too much concentration of A, so that A needs to be used up. Well, that sounds like it needs to be in the reactants, right? Because reactants get consumed or used. So if I add A, because A is on the left side of the reaction, my equilibrium is going to shift to the right. If I were to remove A, okay, well, that means that as you think about it, your system's going to need to produce more of A because you've removed it. You've disturbed the equilibrium by removing A. So in order to produce more of it, that means it needs to be in the product. Okay, so since the A is on the left, my reaction needs to run into this direction to put A in the product so that we make more of it. Okay, the way that I always think about this is I remember away from the added to the removed. And that's the example I just saw there. So if I added A is on the left, it's got to shift away from the added, so the arrow is going to shift to the right, and vice versa. If it was removed, I need to shift towards the removed, again, to produce more of it, so it's going to shift to the left. Now, when I do that, I also need to think about when this shift occurs, when our shift occurs here, right or left, I also need to think about what that does to the concentration of the other things in the reaction. So remember that in this case, so let's say we have a situation in which I've added A and my reaction is going to be moving in this direction. Well, that means not only is that additional A going to be used up, but the concentration of B will go down, and I'll be making more C and D. So those concentrations will go up because our products, because they're products, because of the way the arrow has shifted, and so I will be producing more of those. Last thing here, as we know, pure solids and liquids they are not in our equilibrium expression. So if I change a pure solid or liquid, or disturb a pure solid or liquid by adding more or removing some of it, that does not affect my equilibrium, my shift. So I'll just say does not cause a shift. Now, if there are solids and liquids in the reaction and the concentration of a gas or a solution is changed, forcing the reaction to start proceeding in one direction or the other, then the concentration of the solid and liquid will be affected because the reaction is going. So this idea that it'll be used up or it'll be produced does happen, but a disturbance itself to a solid or liquid would not cause a shift in the equilibrium because it would not disturb it out of equilibrium. All right, so next way to disturb a system in equilibrium is changes in pressure. Key here, remember the relationship between pressure and volume. Because the easiest way for us to affect the pressure of a gas is often by changing the volume of the container. Okay, so just as a review, if you decrease the volume, you increase the pressure. Pressure questions will often be asked in terms of volume changes. So just remember that relationship. Okay. If you are decreasing the pressure, okay, again, you would do that by increasing the volume, correct? Decreasing the pressure, the shift is going to be to produce more moles of gas. Okay, so if I decrease the pressure, the system's going to want to bring the pressure back up. Okay, so in order to do that, we need to have more. The easiest way to do that is to have more gas, so to produce more particles of gas. So my system is going to shift to point in the direction of more moles of gas. Okay, so just the opposite, if I increase pressure, the system has to alleviate that pressure increase. How's it going to do that? It's going to produce fewer moles of gas. So it's going to shift to produce fewer moles of gas. All right, we will see that example here in a minute. Last way to disturb equilibrium is a change in pressure. As we know, change in temperature. As we know, changes in temperature indicate heat flow. So obviously, that if there's a change in the heat of a reaction, then it needs to shift to account for that change. This means that we have to identify. So our first step is to identify the type of reaction. By that, with regards to heat, we're meaning, is it exo or endo? All right, is our reaction exothermic or endothermic? Now, once I understand that, so now there's a couple ways that we can see that. They may just tell us in the following exothermic reaction, right? They could have heat as a reactant or product, so actually written into the reaction as a value in the reactants or the products, or just maybe plus heat or plus energy on one side of the reaction or the other. And finally, they can give me a delta H value. So we know a negative delta H is exothermic, positive is endothermic. Once I've identified whether my reaction is exo or endo, and therefore where the heat is currently located, on the left or on the right, then we're back to away from the added to the removed. Okay, so if the temperature is increasing, and let's just say I have A plus B yields AB plus heat, okay, because the heat is in the product side there, that I know where it is. It's located on the products, right? So if there is a temperature increase, that means I'm adding heat. So in that case, the reaction would shift away from the added. Okay, away from the added. So our first task is to identify where that heat is actually located. This would be the simplest scenario where they actually write it directly in the reaction as a product or reactant. They can also tell me exothermic or endothermic, or they can give me a delta H value. So I should be able to handle all three of those to identify where the heat is located, on the left or on the right. And then at that point, it's away from the added to the removed. All right, so let's look at an example problem here. Why don't you go ahead and pause the video and copy this down in your notes. All right, so let's take a look here. What we want to do is predict the equilibrium shift after each of the disturbances. So SO2 is added. Again, we're changing the concentration. If I notice here, the SO2 is on the left side of our reaction. So we have added more SO2. We want to use that up. It needs to be a reactant. Again, the phrase away from the added helps here. So this is going to shift in the forward or to the right. Okay. Next, we have SO3 is being removed. So we see our SO3 is over here on the right. Again, since it's being removed, the system needs to make more of it. That means it needs to be a product. The phrase to the removed tells me this is going to shift to the right. Okay, next, the volume is decreased. So again, this is a multi-layer here. So volume is decreased tells me pressure is increased. Remember that relationship. As I said, pressure questions are often asked in terms of volume changes. Okay, so pressure is increased. So in order to alleviate that additional pressure, the system needs to produce fewer moles of gas. So it's going to shift to the side with fewer moles of gas. So as I take a look here, I have 2 plus 1 moles of gas, or 3 moles of gas on the left, and 2 moles of gas on the right. So since I have a pressure increase, it's going to shift to the side with fewer moles of gas to produce fewer moles of gas. So this is going to shift to the right. Finally, temperature is decreased. Okay, so we said the first task here is to identify where the heat is located. Is it on the left or on the right? If you got to catch this here, for the exothermic reaction. So that tells me that heat is over here on the right. It's a product. Exothermic produces heat. Okay, so now that I know where the heat is, temperature is decreased, tells me I'm removing heat. So to the removed, I have to produce more heat. This reaction is going to shift. After that disturbance, the reaction is going to shift to the right. Okay, that's our first kind of layer of Le Chatelier's principle. We need to be able to identify which way the equilibrium shift will happen based on the disturbances. We also need to be able to identify, once I've determined my reaction has shifted in a particular direction, the other layer is to be able to identify what is happening to the concentrations of everything in the reaction. So, for example, if I had a shift like this, I would be saying that my concentration of SO2 would be removed, would be going down, my concentration of O2 would be going down, and my concentration of SO3 would be going up, because again, reactants get used up or consumed and products get produced, or we make more of them. So that's the second layer that we'll see in some of our questions as well. All right, that's all for this section on shifting equilibria, Le Chatelier's principle.